Okay. I think, okay, now it's good. I'll post the photos or something. Now it's recording. Okay, great. Yeah, so last time, I think I just, I defined posets and I advertised them and I gave a bunch of examples. Today we're gonna actually do something with posets. Where's my chalk? Here. Okay, so I'm gonna define Rowmotion, which is an operator that acts on what are called the order ideals of a poset. And then we're gonna look at some dynamics of this operator. So this will be about Rowmotion. So, okay, I have to still define a couple things. An order ideal of a poset P is a set I contained in P. And basically it's just a set that's closed downward. So formally I would say such that if x is less than or equal to y in the poset, and y is an element of the order ideal, then that forces x to also be in the order ideal. Okay? And I'll let J of P be the set of order ideals of P. There's also a dual notion, which is what's called an order filter. So an order filter is a subset that's closed upward. So an order filter of P is a set F contained in P such that if x is greater than or equal to y, maybe I didn't define this, but this should be obvious that when I write x is greater than or equal to y, that just means y is less than or equal to x. And y is in F, then x is in F. Okay? And now if I have some set S, so for S, a subset of P, I'm going to let delta of S, maybe I should, do I want to subscript? Yeah, no, just delta of S. This is going to be the set of things that are less than or equal to something in S. So you can think of sort of saturating downward, or in other words, it's like the order ideal generated by S. So this is just the set of X in the poset such that X is less than or equal to Y for some Y in S. And then dually, I'll define nabla of S. So this like upside down delta of S. This is just going to be the set of things that are greater than or equal to something in S. So this will be the set of X in P such that X is greater than or equal to Y for some Y in S. Okay? Okay, so now I can define Rowmotion. So Rowmotion is the bijection, which I'll denote by rho. It's a bijection from the set of order ideals of P to itself. So you give me an order ideal, and this will spit out another order ideal. And it's defined as follows. Well, rho of an order ideal I should be, I want to take the complement in P, so it's going to be P minus something, and this something is going to be the order filter generated by the maximal elements of I, which I'll denote by max of I. And I'll give an example of this. Okay, example. So let's say I take this poset here. Okay, so it's this 6-element poset. And I want to pick an order ideal. So, hold on. Okay. Let's say I pick my order ideal to be these 3 elements here. Okay, so you can see this is closed downward, right? Like for anything in the order ideal, everything below it is also in the order ideal. Then what I want to do to apply row motion is basically 3 steps. So the first step is to take the set of maximal elements of the order ideal. So let me do that here. So taking the max of I well, the set of maximal elements of this order ideal is just this one element here. In general, you could have multiple maximal elements of an order ideal, but in this example, it's just this one element, so I just get this. And then, okay, the next step, I've taken the set of maximal elements. Now I want to basically saturate upward by taking the order filter generated by this one element. So now I take delta of max of I. And that's going to be, let's see if I have room. That's going to be this element and everything above it. So that's just these 2 elements here. And then the last step is I just take the complement inside of P. So P minus that. And this will be well, it's everything else. It's this. And so these 3 steps together are one application of row motion. Okay. So before I say mathematical things, let me just say where this was introduced. So this was introduced by, I think, Duché. This was in 1974, although it wasn't called row motion until recently. And it was studied on Boolean lattices. So when the poset P is a Boolean lattice, it was studied lattices by Brouwer and Schreiber. Schreiber. And this was in 1974 and 1975. Okay, so for most posets, like if you just give me some random poset, the behavior of row motion is probably going to be very wild and unpredictable, and there's not really much we know how to say about it. And by that I mean, like, you can try to say, well, if I iterate this map, if I take row motion of an order ideal and then I get a new order ideal, now I apply row motion to this order ideal and I get another one and I just iterate it, that's going to break the set of all order ideals into orbits, and we're going to want to understand these orbits. But for most posets, like you just start with some poset and you look at the order ideals, this is just like kind of crazy and we don't really know how to understand it. But there are some special posets where people have found that very interesting things happen. So I'll tell you about some of those. Maybe I should explain why it's called row motion. So there's another way of defining this, which is using what are called toggles. So for any element x in my poset, I'm going to define the toggle which will be a map tau sub x from the set of order ideals to itself. It'll be a bijection. Actually, it'll be an involution. And it's defined by saying that tau sub x of an order ideal is, well, basically the point is that if x is in the order ideal, I want to take it out. And if x is not in the order ideal, I want to add it in. The issue is that I'm not allowed to do this if doing that operation creates something that's no longer an order ideal. I want to make sure that whatever I get out is actually an order ideal. And so if doing this thing, which is either taking x out or adding it in, results in something that's not an order ideal, then I just don't do anything at all. So formally, the way to write this would be, this should be the symmetric difference of I with the singleton set x. So this notation just means if x is not in the order ideal, add it in, and if x is in the order ideal, take it out. But you only do this if this thing is actually an order ideal. And otherwise, you do nothing. You just stay with the order ideal I. Okay, let me close the door. Okay. And I guess the point is that, well, okay, Rowmotion I defined here in sort of a global way. You do just like these 3 steps, and composing these 3 steps, which is sort of taking place on the entire poset, gives you Rowmotion. But you could also, there's a way of defining Rowmotion, which I'll do in a second, which is where you compose a bunch of these little toggles, and you can think of these as like little local operators, because they don't really do much. They either add x in or take it out or do nothing, and it's not really affecting the order ideal by that much. But you can compose them and end up getting Rowmotion as a composition. So in order to define how to do this, I need one other definition, which is important. Yeah, maybe I'll do it here. So a linear extension of P is an ordering of the elements of P, basically that preserves the order. Or I could think of it as a bijection. So, okay, maybe I'll say it's a bijection, let's say U, from P to the set of integers from 1 to n. I guess I'm assuming this is an in-element poset. Okay, so P has in elements. And this is such that whenever x is less than y in the poset, that implies that u of x has to be u of less than u of y as numbers. Okay? So if I think of sort of labeling my poset P with u, think of u as like a labeling that assigns a number to every element of the poset, the number should be increasing as I go up the poset. So if I like pick a chain in the poset and I start walking up this chain, the number should be increasing as I go up. And we can also view, okay, so we also view oh, maybe I should define, sorry. So I'll let script L of P be the set of linear extensions of P. Okay, and then, okay, maybe I can fit this. Is it okay if I write here? Can people see this, or should I? Maybe I'll write it over here. Okay. So we also view a linear extension U in L of P as an ordering of the elements, which is just the ordering, say, x1 through xn, where xi is just u inverse of I. Okay. Okay. So any questions up to here about these definitions? Okay. So then the proposition is that you can use these toggles in the order of a linear extension to give a different definition of Rowmotion. So proposition, let x1 through xn be a linear extension of P, then Rowmotion, which I defined over there, is the same as what you get by doing, well, first you do the toggle tau sub x1. So you do this toggle thing at the first element in your linear extension. And then you do, well, tau sub x2, and so on, until eventually you do tau sub xn. Oh, maybe there's one thing I should mention, which is that in a lot of places in the literature, Rowmotion is defined to be the opposite of what like the inverse of what I defined here. So some papers will define Rowmotion to be where you do these steps in reverse. You do the complement and then you take, well, yeah, you take the complement and then you like take the set of minimal elements and then you saturate downward. But I'm just doing it this way, but just, I guess, keep that in mind. And if you did it that other way, then you'd want to use the reverse of a linear extension in this proposition. Okay? So let me give an example of this. Where can I give an example? Let me go back over here. Okay, let me use the same poset that I had before. So here's my poset. And let me pick a linear extension. Doesn't matter which one I choose, but I'll just pick one of them. So maybe I'll choose this to be x1, this will be x2, x3, x4, x5, x6. Okay. So you can see this is a linear extension because, like, as I read off these elements in this order, x1 through x6, I'm never going down, right? I'm just either going sideways or up. So I go x1, x2, x3, x4, x5, x6. And so now let me compute Rowmotion using this toggle definition, starting with this same order ideal here. So I'll start with, what's my red chalk here? So I start with this order ideal. And I'm going to start by doing tau x1. And when I do that, okay, so what does tau x1 do? Well, okay, x1 is this element. So it says, because x1 is in my order ideal, I want to take it out. But if I took it out, this would no longer be an order ideal. So actually, I'm not allowed to take it out. I just have to do nothing. So tau x1 actually just does nothing, and I have the same order ideal. Okay. Now let's do tau x2, which is going to be similar. So this is tau x2. Again, I try to remove x2 from my order ideal, but I'm not allowed to do that, so I do nothing. Okay. Now let's do tau x3. Okay. So now when I do tau x3, I see that x3 is not in my order ideal, so I want to add it in, and I'm allowed to do that, because if I add it in, then what I get is an order ideal. So then I get this. And now, let me do tau x4. Okay, maybe I should ask, what does tau x4 do to this order ideal? Yes?
It will remove x4.
Yep. Yeah, so it removes x4 because, well, x4 is in the order ideal, and removing it gives me something that is actually an order ideal. So then I'm just left with this. Okay. Let's see, what is tau x5? Okay, so what is tau x5 of this?
It's going to add x5.
Yep, yeah, so it'll add x5. So I get this, and then finally, last one is tau x6. Okay, so what does tau x6 do to this? Nothing, right. So now I'm left with this, and if I did this right, this is the same as what we got here with Rowmotion. Okay? So this whole thing was Rowmotion. Okay? So the reason that it's called Rowmotion is because if our poset is ranked, like this one is, then we could pick a linear extension that just goes basically row by row, which is what I did here. I just said, okay, let me make x1 through x3 like the bottom row, and then x4 and x5 will be the second row, and then x6 is the top row. And then when you do Rowmotion with the toggles, you're basically, you can think of it as toggling everything in the bottom row all at once. And this is because whenever you have, let's say x and x prime are incomparable elements, their toggles will commute. Tau sub x and tau sub x prime will commute with each other. This is not hard to see if you just sort of stare at it. And so if I look at the bottom row, well, these elements are all incomparable, so I can really think of just toggling them all at once. And then I go to the next row and I sort of toggle everything here all at once. And then I go to the top row and toggle everything all at once. So it's like I'm going row by row. The reason it's actually called Rowmotion is because there's a different operator called ProMotion, which was introduced by Schutzenberger back in, like, I think the 70s or something. And then Nathan Williams and Jessica Stryker wrote a paper about Rowmotion, and they named it Rowmotion. I mean, it had already been studied, but they gave it this name because they were like, well, you're doing some kind of row thing, but it's like ProMotion, so there's like a play on words. And so now this sort of stuck, and people call it Rowmotion. Yeah. Okay. So yeah, maybe I'll just write down if P is ranked, we can toggle row by row. From top to bottom, or from bottom to top. Okay, so let me tell you an actual theorem about like a specific example of Rowmotion, like on a particular type of poset. Okay, so this is from 1974. Under Brouwer and Shriver. So they showed that the order, maybe I'll define this, the order of Rowmotion acting on the set of order ideals of a product of two chains. So let me just write this and then I'll define the notation here. No, I guess I didn't leave room. Is A plus B. Okay, so what I mean by, so I'll use bracket A for, well, okay, again, that's my notation for just the integers from 1 to A, but I'll also think of it as the chain poset. So when I write this, think of this as like an A element chain. And similarly, bracket B, I can think of as a B element chain. And then this is the product, which is what I defined last time. So this is where, this is the set of elements here is just ordered pairs, where the first thing in the pair is something from this chain and the second thing is something from that chain. And then the order relation is that like u comma v is less than or equal to u prime comma v prime if u is less than or equal to u prime in this chain and v is less than or equal to v prime in this chain. Okay. Maybe actually I can draw a picture of this. It's actually easy to draw what these look like. They basically just look like rectangles. So this would be like the poset bracket 3 times bracket 4, because this is the 3 elements and this is the 4 elements. Okay. And okay, what do I mean by order? Well, this is just going to be the least common multiple of the orbit sizes of Rowmotion. So if you think of Rowmotion as splitting the set of order ideals into a bunch of orbits, then this is the least common multiple of the orbit sizes. Or you could really just think of this as it's the smallest positive integer, say omega, such that if you do Rowmotion omega times, you'll always get back to where you started. Okay. So maybe I'll just say this is the smallest positive integer omega, such that if I do Rowmotion omega times to any order ideal, I just get that order ideal back. Okay, and this is kind of surprising because, the way I define Rowmotion is, well, the first definition was this kind of weird thing where you do this 3-step procedure and it's sort of mixing things up in a weird way. And then also this definition using the toggles, it's kind of this strange thing where you have like all of these local moves that are being composed together. And so you might expect that Rowmotion should just be kind of wild and chaotic, which it is for most posets. But in this case, it's very nice, and you can get this very nice, simple formula for the order. If you took like a usual, well, like sort of a random poset, like if I just kind of added on a couple elements here in some weird way, probably I would expect the order to just like be some crazy thing. It'll probably have large prime factors and it'll be just like not really well behaved. But here it's very well behaved. Okay. Okay, so I'll actually prove this, and I'll give a proof that's due to Richard Stanley. So maybe I'll do that over here. Okay, so this is a proof by Stanley from 2009. Okay, so let me define script W sub A, B to be the set of words over the alphabet 0, 1, so these are just binary words, for words over 0, 1, that use exactly A zeros and B ones. And I want to define a very simple map from this set of words to itself, which I'll call rot. And this is for rotation. So define rot from WAB to WAB. And all this does is it takes some word, which maybe I'll write as a, oh yeah, okay. So rot of some word, let's say x1, x2, dot, 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 x, a plus b. Right, so every word in this set has a plus b letters because it has a zeros and b ones. This is some word. This is just going to be, well, x2, dot, 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 x, a plus b, x1. So I just cyclically rotated the word by taking the first letter and moving it to the end. Okay. So this is very simple. We understand this map very well, like there's nothing complicated going on, you're just moving the first letter to the end. And we're going to try to relate this very simple operator to Rowmotion, which seems more complicated. Okay, so for an order ideal I in J of my product of two chains, I'm going to let ST of I be this word. Okay, so I'll just write W1 through WA plus B. This is some word. And the way I define the letters, well, it's a little weird, but it's fine. So where W sub I is going to be, there are three cases. It'll be 1 if 1 is less than or equal to I is less than or equal to A, and the set of maximal elements of my order ideal contains an element of the form I comma k for some k. Okay. So again, I is an order ideal of J of bracket A cross bracket B, so you can think of it as a certain subset of this poset. The elements of this poset are ordered pairs, where the first thing is a number from 1 to A, the second thing in the pair is a number from 1 to B. And all I'm saying here is, if I is between 1 and A, and the set of maximal elements of my order ideal contains some ordered pair that starts with I, then I define WI to be 1. Similarly, I'm also going to define it to be 1 if A plus 1 is less than or equal to I is less than or equal to A plus B, and the set of maximal elements of I does not contain an element, does not contain an element of the form k comma I minus A. Okay. Okay, so now I'm just saying I is between A plus 1 and A plus B, and the set of maximal elements does not contain an ordered pair that ends with I minus A. And notice that I minus A should be something between 1 and B, so this kind of makes sense. And then it's 0 otherwise. Okay. Then this word, ST of I, is called the Stanley-Thomas word of I. So the word ST of I is called the I. Okay, so maybe I can fit the rest of the proof in this box. So the claim that I want to make is that this map, okay, so I have ST. Think of ST as a map that takes an order ideal and gives me a word. Well, this word, if you stare at the definition, you can check that it is in the set W sub A comma B. Maybe I'll do an example and that'll make it more clear, but if you just sort of stare at it and you think about it for a second, you'll see that there should be exactly A zeros and B ones. So this is actually a map from J of bracket A cross bracket B to script WAB. Okay, so it's a map. It's also a bijection. And it's what would be called an equivariant bijection, meaning that it basically intertwines this rotation operator that we understand with the Rowmotion operator. Or to write this formally, moreover, if I do Rowmotion to an order ideal, and then I take the Stanley-Thomas word of that order ideal, that is the same thing as taking the Stanley-Thomas word of the original order ideal and then rotating it. Okay. And then if you believe this claim, oh, maybe I'm not, wait. Yeah, maybe I won't prove the claim, but I'll give an example. I'll try to illustrate it with an example that should indicate why it's true. But if you believe this claim, then the proof should follow the fact about the order being A plus B, because, well, this is telling us that the orbit structure of Rowmotion should be exactly the same as the orbit structure of rotation, because you have this map, this bijection that's sort of just transferring one of these operators onto the other. So then, okay, so the proof follows since the rotation operator obviously has order A plus B. And so obviously if you take a word of length A plus B and you rotate it A plus B times, you just get back to where you started. Okay? So I'll try to justify this claim with an example. Do you think it's, maybe I'll try using this board. We'll see how it works. You're gonna have to think on your feet, Okay. So, example. Okay, so let's say A is 4, B is 3, and here's my poset. And let me pick an order ideal. How's the camera working? Okay, the next step, okay, A is 4, so again, if I look at W3, 3 is between 1 and 4. So I ask, is there a maximal element that starts with a 3? Yes, there is, it's this one, so I have another 1. And then for W4, 4 is between 1 and A, because A is 4. There is no maximal element that starts with a 4, so this gives me a 0. And now I need to finish the word, but now I'm going to go to like the second case there in the definition of WI. So I say, okay, now when I is 5, 5 is between A plus 1 and A plus B. And so I ask, does the set of maximal elements not contain an element of the form k comma 5 minus a. 5 minus a is 1, so I want to know, is it true that the set of maximal elements does not contain something that ends with 1? No, it is not true. It is not true that the set of maximal elements does not contain something that ends, that ends with 1, because it does contain something that ends with 1. So it's a 0, which is what I wrote in my notes, so I think that's true. Okay, yeah, you gotta think about it for a second, but okay. Now for I equals 6, what do we do for I equals 6? Is it true that the set of maximal elements does not contain something that ends with 2? Yes, it is true that the set of maximal elements does not contain something that ends with 2. So I write a 1. And then finally for 7, I say, okay, is it not true that the set of maximal elements contains something that ends with 3? No, it does, so I write a 0. Okay? Okay. Hopefully that's okay. Let me do Rowmotion to this. Okay, so I'll draw my... I don't know if this is actually justifying the claim. I think it's just an example. And then you just kind of have to stare at it on your own time to sort of convince yourself that the claim is true. But we'll at least do the example. Okay. Okay, so what is Rowmotion of this? Well, let me do the original definition, which I've erased by now. But the original definition says I should take the set of maximal elements, which are these 2 elements here. Then I saturate upward, which gives me these 2 elements and everything above them. So all of those 7 elements. And then I take the complement of that, and that should give me these 5 elements here. So if I do Rowmotion, I end up with this. Okay? And now let's do the Stanley-Thomas word of this. Okay, maybe I'll do this a little faster. If I is 1, then, okay, does the set of maximal elements contain something that starts with a 1? Well, okay, what are the maximal elements? Maybe I should write those down. This one is 2, 2. And this one is 1, 3. So the set of maximal elements does contain something that starts with 1. So the first letter in my Stanley-Thomas word is 1. And it also contains something that starts with 2. So I get a 1. And then the set of maximal elements does not contain something that starts with 3. So I get a 0. And then it does not contain something that starts with 4. So I get another 0. And now I do the confusing thing where I ask if 5 is, well, okay, if the set of maximal elements does not contain an element that ends with 5 minus a, which is 1, it does not contain something that ends with 1, so that is, I get a 1. And then because the set of maximal elements does end with something that ends with 2, or it does contain something that ends with 2, I write a 0. And then it does contain something that ends with 3, so I write a 0. And that gives me this Stanley-Thomas word. And finally, if I did this right, this word is what you get from this word by just moving this 0 over to the end. Okay? Okay, cool. And yeah, so I think to justify this in your head, you sort of stare at it and then you sort of realize at some point why this makes sense. But I think you kind of have to just think about it. Okay? Does that work? Okay, maybe I'll go back to these boards because I realize this is a mistake. Okay. Any questions? All right, let me tell you more. Let me tell you about another family of poset chains. But actually, I'm going to generalize this example. So this is what's called the root poset of type A3. And more generally, you can define the root poset of type AN. And actually, I'm not going to define it, but you'll see what it is because I'll draw the examples. Okay, so the definition here, so the notation is phi plus of AN be the root poset of type AN. So the terminology and the notation here is coming from the theory of root systems, and these are related to Coxeter groups and semi-simple Lie algebras and algebraic things. I'm not needing that for the definition of the poset, because actually the posets end up being very simple, but that's just why there's this sort of weird notation for it. But okay, so this is the root poset of type AN. And I'll just draw the first few of them and you'll see what they are. So phi plus of A1 is, well, let me do it this way. Phi plus of A1 is just a single element. Phi plus of A2 is this poset, 3 elements that look like that. Phi plus of A3 is the one that I had before. It's this thing. Let me do phi plus of A4. Actually, it's not hard to define this. Maybe I can, but I think the pictures indicate it pretty well. Let's see. Oh, maybe I did this bad. Oh, wait. Okay, hold on. Yes. Okay, so hopefully you can see what I'm doing. One way you could think of it recursively, I'm just, at each step I add on sort of another layer and attach it like this. Okay. Is this clear, or should I draw phi plus of A5 as well? Okay, maybe it's clear. Okay, so this is the root poset of type AN. Okay, so here's a theorem. This is due to Armstrong, Stump, and Thomas. And this was in 2013. Oh, I don't know if I have enough room. Okay, we'll see. So first of all, the order of Rowmotion on the set of order ideals of the root poset of type AN is 2n plus 2. So it's a very simple order. And actually you can say something a little stronger. So in fact, if you apply Rowmotion n plus 1 times, what this does is it flips your order ideal across the vertical axis. Right, so you imagine maybe I have this, and there's this obvious, vertical set or the symmetry that I can reflect about the vertical axis. And if I take any order ideal, then I can just reflect that order ideal and get a different order ideal, another order ideal. And what this is saying is that if I do Rowmotion n plus 1 times, which here that would be 5 times, then that just flips my order ideal. And so then, of course, if I do that again, then I just get back to where I started. And then there's one other thing.
Colin?
Yes?
So does it mean like for A1 you would have to do 4 times?
For phi plus of A1?
Yeah.
Oh. Yes, good point. Okay, maybe I want to not do n equals 1. Let n be at least 2. Okay, I think, yeah. So I don't want to do this for n equals 1. Let's just ignore that one. But I think this makes sense for this. Is that right if I do this? Six times? Yeah.
There are only three
No.
order ideals.
Yeah, yeah, wait. There are only 3 order ideals. Do I have the numbers wrong? Maybe I have the numbers wrong.
Should it be 0 indexed?
Let's see. So the number of, no, wait, no, there shouldn't be, no, there's the empty order ideal, yeah, there's the empty, okay, yeah. I think it's fine. Let me draw all of the orbits for that. Let me do that over here. And I just said that I wasn't gonna come over here, but, so, there's, okay, so there's the empty order ideal, and then there's the full order ideal, which has everything, and then there's this one, and then there's this one, and then there's this one. And I think what the orbits do is this one here goes to the top, and this top one goes down here. So there's one orbit of size 2, and then these get permuted among themselves. So I think this one, if I take, okay, so I have to saturate upward and take the complement, so I get this. No. Sorry. No, okay, these get switched between each other. Yes, okay, my bad. Okay, this one, the set of maximal elements is empty. So I take the empty set, I saturate upward, I get empty, and then I take the complement, which gives me this. Here, if I do Rowmotion, I get this one. And here, if I do Rowmotion, I get that one. I think that's what happens. Yeah, okay. So there's one orbit of size 2, there's one orbit of size 3, and the least common multiple of 2 and 3 is 6, which is 2 times 2 plus 2. Okay, yeah. Okay, yeah, thank you. So I think it does work for n at least 2. Okay, let me add one other thing to the theorem here. For every orbit, let's say O, script O, of Rowmotion, we have, okay, I'll try to write it down here. If you take this quantity, 1 over the size of the orbit, and then you sum over all of the order ideals in the orbit of the number of maximal elements, okay, this is kind of surprising, this is always n over 2. So basically there's this statistic that you can define on order ideals, which is just how many maximal elements does it have. And what this is saying is that if you go along any orbit of Rowmotion, the average of that statistic along that orbit is always n over 2, independent of what orbit you choose. I should also remark that the actual theorem that they proved was more general, because they prove it for any finite Weyl group. Here I'm just working in type A, just like corresponding to the symmetric group, but there is a more general statement that they prove. Let me give an example of this last part here. I guess I could do, well, okay, we could do the example there, but let me do the example for n equals 3, because I think it's a little more illustrative. Okay, so let me just write down some orbit of Rowmotion. Let's say this order ideal. And now I want to do Rowmotion to this. So I take the set of maximal elements, that's just this element. I saturate upward, so I get these two elements here. Then I take the complement of those two elements, and that gives me these four elements down here. Okay. Okay. So I think this orbit has size 8, so I'll draw all 8 of them. Okay, the maximal elements are these two elements. I saturate upward, I get all 4 of these elements. I take the complement, and I'm left with these 2 elements here. Okay. The maximal elements are these 2 elements. I saturate upward, so I get all of these elements except for this one. So then when I take the complement, I get just that one. Now, the maximal elements are just this. I saturate upward, I get these 3 elements. When I take the complement, I'm left with these 3 over here. And okay, maybe one thing I should note is that I've now done Rowmotion in +1 times, because in is 3, and I've done it 4 times. And you can see I've just reflected what I started with about the vertical axis. So now, well, now it's pretty obvious. I mean, I could do this thing again where I say, oh, the maximal element is this. I saturate upward, I get these 2. I take the complement, I get these 4 elements. Or I could just say, like, obviously, whatever, like, even if you don't believe this theorem, you should still believe that if I do Rowmotion to this thing, I should get the reflection of what I got when I did Rowmotion to this thing, because everything is just symmetric about reflecting. So I should obviously be getting whatever the reflection of this is, which is this here. Okay, and then now I should be getting the reflection of this thing. Now I should be getting the reflection of that thing, which is just this element. And then finally, I should get back to where I started, because I'm now getting the reflection of that one. Okay. And so now I want to look at this last part of the theorem, which says that if I take the average of the number of maximum elements along this orbit, I should be getting n over 2. So here, the number of maximal elements is 1. So I'll write a 1 there. Here, the number of maximal elements is 2. So 2. This has 2 maximal elements, these 2. So I write a 2. This has 1 maximal element. So I'll write a 1. This has 1 maximal element. So I write a 1. This has 2 maximal elements. So I write a 2. This has 2. And this has 1. And then if I add these up, 1 plus 2 plus 2 plus 1 plus 1 plus 2 plus 2 plus 1, and I divide by the size of the orbit, which is 8. Okay, what is this? 3, 5, 6, 7, 8, 9, 10, 11, 12. 12 divided by 8 is, so 12 divided by 8 is 3 over 2. And that is n over 2. Okay? So I think I won't prove this theorem, because it's actually quite involved. But yeah, it's a cool paper. Yeah, so I won't prove it, but maybe I should comment on this last part, what this is called. So this motivated Jim Propp and Tom Roby to define what they call a homomessy. So I can actually define that more generally. So this is like one of the key definitions that people like in the field of dynamical algebraic combinatorics. Okay, so very generally we can just say let X be a finite set. And let F from X to X be some bijection. So we'll think of this as like an operator that we're going to iterate, and then we can look at the orbits of F. So it breaks the set X into orbits. And then we'll say a statistic statistic. I'll just call it stat. So stat will be, by a statistic, I really just mean it's a function from X to, let's say, the real numbers. We'll say this is homomessic if, I'll say it's homomessic for F if there exists some constant C in R such that whenever I take the average over some orbit, so I'll just write this. So the average of this stat of X over some orbit of F should always be C. So for every orbit O of F. And yeah, I'll just say this definition is due to prop and Roby from 2015. So the kind of strange thing about homomessy, so this is one example. The last statement here, you could say, this is telling us that the statistic that takes an order ideal to the number of maximal elements of that order ideal, that statistic is homomessic for Rowmotion, well, on the type A root poset here, and that C value is just n over 2. The kind of surprising thing is that this shows up in a lot of places. So this is kind of a strong condition if you think about it. It's like, why would this actually happen? Why would the averages all be the same? But there are a lot of examples, and there's sort of a lot of papers that just find various examples of homomessies in, for a bunch of interesting dynamical systems to find on interesting combinatorial objects. In fact, I think there's a paper somewhat recent that goes through some database and sort of searches through the database of like interesting combinatorial objects and operators on them, and just like exhaustively searches for, well, not exhaustively, but in some way searches for homomessies and finds just like this long list of them, and it's kind of surprising that they are as prevalent as they are. Okay? Yeah, so maybe I'll just say in writing what I was just saying. So, by the previous theorem, the map that sends I to its number of maximal elements is homomessic for Rowmotion, but of course this is just on the order ideals of phi plus of A n. Okay. Okay, so homomessy is like one thing that people study in dynamical algebraic combinatorics. There's also another sort of well-studied thing that has a nice name, which is called the cyclic sieving phenomenon. So I think I'll define the cyclic sieving phenomenon, and then I don't know if I'll have time to state a theorem about it, but then I'll tell you maybe next time a theorem about an example of the cyclic sieving phenomenon. Okay. Let's see. Yeah, maybe I'll erase this. Okay, so let's say C sub omega be a group. It's a cyclic group generated by some element G, because this is a cyclic group of order omega. And let's say it acts on some finite set X, acting on a finite set X. And I'm going to imagine I have some polynomial f of q. This is just some polynomial with, say, complex coefficients in the variable q. So following, there's this now famous paper by Reiner, Stanton, and White. So following Reiner, Stanton, and White, we will say that the triple X C omega f of q exhibits the cyclic sieving phenomenon. Or we can abbreviate this to CSP. If for every integer k, we have, okay, so I'll write this down, then I'll explain what it means. F of e to the 2 pi I k over omega equals the number of elements of x that are fixed by the action of g to the k. Okay. So let me just explain what this is saying. If you want, you could think the action of this cyclic group is like having some operator that is acting on your set. So you could think maybe we have Rowmotion acting on the set of order ideals of some poset, and let's say omega is the order of Rowmotion. So then you just think, well, G is acting by applying Rowmotion. Okay, so this is like the action of the cyclic group of order omega on the set X. X here would be the set of order ideals. And the goal, like one of the big goals in dynamical algebraic combinatorics when you have one of these operators is you say, well, I want to understand the orbit structure. One way of understanding the orbit structure is to say, what is the order? That's what we did, with these theorems where I was saying, okay, so I've erased them, but I said, for the rectangle, we got something of order a plus b. For the type A root poset, we got something of order 2n plus 2. So that's telling you about the least common multiple of the orbit sizes. But you can ask for something more refined where you say, well, maybe I want to know the entire multi-set of orbit sizes. Like, what are all of the numbers that describe the various sizes of the orbits? And when you have the cyclic sieving phenomenon, all of that information is encoded by this polynomial f. Because what this is saying is you have some polynomial, and if you plug in this root of unity, e to the 2 pi I k over omega, that tells you how many elements are fixed by g to the k. In other words, it's telling you how many elements are in orbits of size dividing k. And if you know the number of elements that belong to orbits of size dividing k for every k, you can do some kind of Mobius inversion if you want to figure out the orbit sizes. But in some sense, this is encoding the entire orbit structure with just this polynomial. So I should say that for any operator on some finite set, like you have this setup, there will be some polynomial that does this. You just do some kind of polynomial interpolation thing, and like, so there will be some polynomial that gives you the cyclic sieving phenomenon. But in many cases, it's probably just like some mess, and it's like not a nice thing. So the case where people actually are interested in this is when this polynomial f is very nice. Maybe if it has some nice product formula, for example, or if it's the generating function that counts objects according to some statistic. Okay, so those are like the interesting examples where people want to have a cyclic sieving phenomenon. They say, oh, okay, we have like the orbit structure for some reason is being encoded by this nice polynomial that has like this factorization or something. So I'll give examples of this next time, but I think, what time is it? Yeah, I think I'm out of time. So I think that's all for today.